In this video, we're going to discuss Text-to-SQL, its limitations, and two techniques we can use to improve the performance of our Text-to-SQL methods. Text-to-SQL is a technique used to generate SQL over a given database from a given natural language question. Given that Text-to-SQL is just translating English to SQL, you would think that modern, state-of-the-art LLMs would be able to solve this quite easily. However, in practice, there are nuanced and varied ways in which this can fail. To be able to measure the performance of different text-to-SQL methods, the Spider benchmark and paper was introduced in 2019. This included over 10,000 questions across 200 different databases. This was challenging for the state-of-the-art techniques of 2019. As you can see, even on the easy version of the Spider benchmark, many of the methods at the time scored around 30% accuracy. However, by early 2025, GPT-4o and other models were scoring 85% plus on this benchmark when used in different text-to-SQL methods. As a result, in early 2025, a more challenging benchmark, Spider 2.0, was introduced. Although GPT-4o and other models were achieving over 85% accuracy on the original Spider benchmark, businesses were still getting unreliable and inconsistent results from text-to-SQL. The Spider 2.0 paper and benchmark managed to recreate these issues by creating evaluations that were made up of samples from enterprise databases across platforms that enterprises use, such as BigQuery and Snowflake. Previous benchmarks included clean pre-prepared schemas, which is why businesses weren't able to see the same results, as their real data was much messier and included field names that were poorly named or ambiguous. As a result, a text-to-SQL technique that achieved 91.2% on the Spider 1 benchmark was now achieving only 21.3% on the Spider 2 benchmark. Now that we were back to state-of-the-art models and state-of-the-art text-to-SQL methods achieving low scores on text-to-SQL benchmarks such as Spider 2.0, techniques to help improve this performance were beginning to be introduced. Apex-SQL is a paper that was introduced in early 2026 that introduced the type of agentic exploration to improve the performance of text-to-SQL methods. Apex-SQL has an advantage over other techniques that cover the entire database schema. By covering the vast scale of a database, this introduces noise and also incurs an unnecessarily heavy token cost for a given text-to-SQL method. Also, previous approaches rely on static representations of a schema, which allows field names to be misleading. To tackle this, Apex-SQL allows an agent to explore the data contained within the table so that it can verify its initial assumptions about what a field represents, and this helps it select the correct fields before attempting to write a SQL query. In this video, we're going to look at two of the steps covered in Apex-SQL. These two steps are both used to prune the schema, which helps reduce the noise and the token cost for a given text-to-SQL method. These two approaches are called logical planning and dual pathway pruning. Before showing how these can be achieved, we next need to introduce a Python module named piglets. Piglets is an open source modular text-to-SQL toolkit, and it's compatible with a variety of LLMs and database providers. Piglets contains a planning model and a pruning model. In the planning model, there is an implementation of logical planning, which we're going to cover shortly, and in the pruning model, there's an implementation of dual pathway pruning, which is the type of pruning that's implemented in the Apex-SQL paper. Logical planning is the first step in the Apex-SQL paper. Logical planning involves instructing a large language model to create several steps in how it's going to tackle the problem of working out what SQL needs to be written. To ensure this produces the best possible answer, the Apex-SQL paper errs on the side of maximizing recall. One particular logical plan may be missing a step that involves a key field. To ensure we don't miss that key field in our plan, we generate a sample of n logical plans before aggregating them into a master plan. Here are the prompts we use to create the draft logical plans and then also the aggregate plan, which we create by putting the logical plans together. These prompts come directly from the Apex-SQL paper, which I'll include a link to in the notes. The logical planning system instruction instructs the LLM to break down the user's question into abstract logical steps. This is performed without the LLM having any knowledge of the actual schema to avoid this planning step being polluted by misleading field names. The system instructions for the aggregation step instruct the LLM to cover all conditions, filters, joins, and aggregations required. This means that if a field is contained in one of the draft logical plans, it is unlikely to be missed from the aggregated master plan. So now it's time to see how we can use piglets to perform logical planning against a natural language query for a given database. Piglets is a modular text-to-SQL toolkit which can be installed using pip or any other package manager in Python. Piglets is open source and includes examples on its GitHub page, such as a dual pathway pruning example here. To show you how logical planning can be achieved using piglets, I've just cloned the repo and I'm going to go through the example that's included in the examples directory. Because I've cloned the repo, I'm first going to run this cell so that I can import piglets from the same repo that I'm in right now. However, in your project, you can just pip install piglets and import it the same as you would any other Python module. My particular example is using GPT 5.2 and a dataset that I've cloned into my BigQuery project. Therefore, I'll be installing the optional OpenAI and BigQuery dependencies too. Instructions on how to do this are contained in this cell. The database name here, Stack Overflow, corresponds to a dataset that I've cloned into my BigQuery project. You can see here that this Stack Overflow dataset contains many tables, and each table contains several columns. You can also see in the description that this comes from a public listing, which is located here in BigQuery data sharing. You can use this example notebook against different databases and different schema names. So if you don't want to clone the Stack Overflow data for this example, you can still use other data sets that you've already created. Next, I'm going to run this cell to set my variable names. The question I'm going to ask is which tags saw the largest increase in average answer score from 2022 to 2023, considering only questions with at least 5 answers. The correct answer to this question is a relatively complex SQL query, as several filters and aggregations have to be performed in the correct order. To create a logical plan, we import the logical planner from the piglets library. We initialize our logical planner by passing it the name of the model that we want to use. You can also provide the provider name. However, with the most popular models, the provider name will be inferred from the model name. So here, I only have to provide GPT 5.2 because OpenAI, being the model provider, is inferred. Next, I provide our question and the sample size that I want to the plan method. I've asked for a sample size of 3. That means the planner is going to generate 3 draft plans before aggregating them into a final master plan. Now that that's finished running, I can run the next cell to inspect the results. Here we can see the natural language question that we asked, and then 3 different logical plans that were generated prior to the aggregation step. As you can see, we have 3 sample plans that have all approached the question in a slightly different way. But our logical planner has aggregated these 3 plans in a way that covers all of the points that were raised in the 3 separate logical plans. The next technique from Apex-SQL that we're going to discuss in this video is dual pathway pruning. Dual pathway pruning tasks an LLM with creating a preservation set of tables and columns that it believes to be relevant to the natural language question, and it tasks the LLM with creating a deletion set of tables and columns that it believes are obviously irrelevant to the natural language question. Once we have a deletion set and the preservation set, we then follow this formula to create our pruned database. So looking at the formula, we take D, our original database, and we subtract from D the deletion set. So we take away from D any of the tables that are obviously not relevant and any of the columns that are obviously not relevant. Once we have the remaining tables and columns, we then union that set with the set of tables and columns that our LLM deemed to be relevant to the natural language question. The result of this is our pruned data set. Another way of visualizing this is using a Venn diagram. If you look at the flow of information on the screen, we start with a natural language question, and if we want, we can also add an aggregate logical plan, as this will help the LLM make a decision as to what is relevant and what isn't relevant. The deletion set and the preservation set may have tables or columns in common, and that's the overlap in the Venn diagram in the middle of this flow. Then on the right hand side, after we prune the columns, what we are left with is everything that either isn't in the deletion set or is in the preservation set. And that's how we use dual pathway pruning to reduce the size of our database before tasking our LLM with creating SQL from a natural language question. Here are some example system instructions that you would use for this stage. These come from the Apex-SQL paper and can be found in the appendix. Something to point out here is that the instructions for the preservation set ask for the LLM to return relevant tables, so these are entire tables that the LLM believes to be relevant, and then also relevant columns. So these are columns that the LLM believes to be relevant. However, the instruction for the deletion set uses much stronger language. It asks for obviously irrelevant tables and obviously irrelevant columns. Again, this is because Apex-SQL errs on the side of maximizing recall. It would much rather include a column that wasn't meant to be included than delete a column that we needed to get the final answer correct. So now it's time to look at how we can use piglets to perform dual pathway pruning on our database schema. So I've just headed back to the notebook that we've already used for logical planning, and I'm just going to continue running the cells following on from the ones that we've already run. To do this, we import the database connector from the piglets library, and we pass to the database connector our database type, which in this case is BigQuery, and our database name. In BigQuery, database name corresponds to the name of our data set, which was Stack Overflow. So we run this cell to connect to our database and retrieve the database schema. Now that that's finished running, we can run the next cell to inspect the schema. We can see that the database connector has retrieved all of our tables, their columns, and their respective data types. All of these are going to be made available to our LLM when performing dual pathway pruning, which is when it's going to create a preservation set and the deletion set. To perform dual pathway pruning, we import the pruner from the piglets library, and we pass the pruner the model name, because this step is going to rely on an LLM. After doing that, we then call the dual pathway pruning method whilst giving it the natural language question and a database object, which is the result of our database connector, which is just our schema that we displayed above. We're also going to give this the logical plan that we made earlier. Now that that's finished running, we can inspect our pruned database. We can see that the pruned database is significantly smaller as it only includes 4 tables, and tables such as posts and tags look like ones that will be relevant to our natural language question. So as you've seen, you can use piglets to increase the performance of your text-to-SQL pipeline. Piglets is designed with modularity in mind, so if we only want to use logical planning, then it's easy to import the planner and just perform the logical planning. This is also the case for dual pathway pruning, and there are also many other methods coming soon.